Hello everyone. Welcome to the week 7 of problem solving session for the NPTEL course Material and Energy Balances. Here in this week, we'll continue with some more energy balance problems. Then the previous 6 weeks, we have completed the first part of the course. Now we are progressing more and more detail in the topic of energy balances. A brief introduction about myself. I'm a PhD scholar in the Department of Chemical Engineering. If you have any queries, feel free to reach out. Please post any queries that you have related to this course in the course discussion forum. Every Saturday, like today, the sessions will be taken from 3 to 5 p.m. and all the sessions are recorded and will be available in my YouTube channel. The link can be found here, as well as notes. The notes and all the recordings will be made available to you in the NPTEL course forum. Let's start with the questions on energy balance. We have in the previous class we have looked into both open system as well as closed systems. We'll try to solve a few problems based on those concepts today, and then we'll move on and solve few more concepts related to heat, specific heat, and various other topics. All right. This is the first question. It reads, changes in the heat input that spacecraft encounter constitute a threat both to any occupants as well as to the payload of instruments. If a satellite passes into the Earth's shadow, the heat flux that it receives may be as little as 10% of that in direct sunlight. Consider the case in which a satellite leaves the Earth's shadow and heats up. For simplicity, we will just select air in the spacecraft as the system. First thing to note is the system is air in the spacecraft. The spacecraft hold around 4 kg of air at 20 degrees Celsius. The air has an internal energy of 8 into 10 to the power 5 joule per kg with reference to fixed datum conditions. And energy from the sun's radiation enters the air as heat until the internal energy is 10.05 into 10 to the power 5 joule per kg. So we have to first calculate how much heat has been transferred to the air. Okay. And part B asks you if the machinery in the spacecraft does work 0.1 10 to the power 5 joule of work on the air over the same interval, how would your answer to part A change? All right. Let's start. So in this question, first thing to note is change in kinetic energy is 0, and also change in potential energy is 0. So if you remember the equation, energy balance equation, for closed system which we discussed last week, it is delta E is equals to delta U plus delta K plus delta P. Now these two parts are already 0. So we are left with only the internal energy part. Alright. And you know, internal energy is equals to Q minus W. So for the first part, A part, W is 0, means there is no work done or done by the system, done by air or done on the air. So delta U is equals to Q, right? So we know the change in internal energy. So initially the air has an internal energy of 8 into 10 to the power 5. Initially it was 8 into 10 to the power 5. And the final internal energy becomes 10.05 into 10 to the power 5 kilojoule, joule per kg. Okay, so these are specific quantities. Please make note of that. Hmm. So we should appropriately put a hat over as well. So if you solve this particular expression, you should get 2.04 into 10 to the power 5 joule per kg. This is your heat transferred, okay, for 1 kg. So since total mass of air in the spacecraft was 4 kg, so for 4 kg of air, heat heat transferred is 2.04 10 to the power 5 into 4. It is 8.16 into 10 to the power 5 joule. Okay. Now let's look at part B. In part B, it is saying that the spacecraft does work on the air. So work will be a negative sign. The value of work will accompany a negative sign. So it will 0.0, 0.11, 0.11 to 10 to the power 5 joule. Okay, that is the amount of work that has been done. From the previous part, you know delta U is equals to Q minus W. So you have calculated the value of Q from part A. You know the value of, sorry, um, you have to find the value of Q. What is the new value of Q for part B? It will be something like this. So you know the value of W, it is 0.11 on 10 to the power 5. What will be the value of U? So U is basically the net energy stored in the system. So from part A, we will take this value as U. All right. So what is the final value of Q? It will be 8.05 to 10 to the power 5 joule. Okay. So here, did you understand why Q in part A was taken as a change in the internal energy? Yeah. So if you see in part A, delta U cap is equals to Q cap. So the Q value that we got is actually due to change in the internal energy. So that is why in part B we took delta U as this value that we obtained from A. Right? Let's move to the next question. So water is being pumped from the bottom of a well that is 15 feet deep at the rate of 200 gallon per hour into a vented storage tank. To maintain a level of water in a tank that is 165 feet above the ground. And to prevent freezing in the winter, a small heater puts 30,000 BTU per hour into the water during this transfer from the well to the storage tank. Heat is lost from the whole system at the constant rate of 25,000 BTU per hour. So, what is the temperature of water as it enters the storage tank? Assuming that the well water is at 35 degree Fahrenheit. So, a 2 horsepower pump is being used to pump the water, and about 55% of the rated horsepower goes into the work of pumping, and the rest dissipated as heat to the atmosphere. So this question sounds pretty straightforward, but this is a energy balance problem on an open system. So let's try to visualize the system first by drawing a diagram. So there is a tank. Wait, let me. So there is a overhead tank which is at some height from ground. This is your ground level. There is a pump that is pumping the water. This is your tank. So the question states that uh, the water is at 15 feet deep. Okay, so 15 feet deep, whereas tank is 165 feet above the ground. This is your water pump. This is your water, right? And there is a small heater as well that puts some heat into the water as it is being transferred to the storage tank. So there will be some heater like this that adds Q to the water. Okay, this is the pump with 2 horsepower that can do 2 horsepower worth of work. So let's write the energy balance equation for an open system. If you remember, this was the general form. Now there is no accumulation of energy, so delta E is 0. There is fixed mass of water that is being transferred from the well to the tank. The water that is present in the inlet has kinetic energy of 0. Water at well inlet, kinetic energy is 0. And the water which is leaving the tank, here there is some pipe that is going to leave, that also has kinetic energy 0. So net, if you net kinetic energy for the entire system becomes 0. So if you put these values in the balance equation, you will find delta enthalpy, change in enthalpy plus change in potential energy is equals to Q minus W. Now, how much water is being pumped? Around 200 gallon per hour. Okay, so first let's convert gallon, which is a unit for liquid. So as I was saying, 200 gallons per hour is the water that is being pumped. So gallon is a liquid, is a unit for liquid. So let's convert into mass. All right. So we can make the calculation later on easier. Total water pumped is 200 gallon per hour. So 1 gallon is actually 8.33 pound. So it becomes 1,666 pound per hour. This is the total water that is pumped per hour in mass form. So what is the change in potential energy? Delta P can be also written like this when you multiply with the mass. Definition of for the definition of the potential energy, I wrote it like this. Okay. So we now know the total water that is being pumped per hour, the mass of that we now know. So we can fit its value in this formula per hour. G, that is acceleration due to gravity. In British unit system, it is actually 32.2 feet per square. And what is the height? So it will be 15 plus 165. That is, if you see, it is 165 in the, if this is the zero axis, 165 let me write it like this. So this is the initial height, this is the final height. So 165 minus, it is a final minus initial minus 15. This is how you will write the change in the height that has happened in feet. Okay. Now we can convert the units to energy units, convert the units to BTU per hour. So for that, we need to add some more units here. 165 plus 15, 180 feet. Now 1 lb force, it is in SI, it is equivalent to Newton, is 32.2 pound feet per second square, and 1 BTU is 1 lb force into feet. So when you solve this, you should get change in potential energy as 386 BTU per hour. Okay, so in this expression, we now know delta P cap. Okay, next, what is the heat amount? Let's calculate Q. So net heat exchanged. Now, initially, so the small heater, it adds heat that is around 30,000 BTU per hour. And some heat is lost as well at the rate of 25,000 BTU per hour. So net heat exchanged, Q will be 30,000 minus 25,000. That is 5,000 BTU per hour heat is net remaining within the water. Okay. Then some work is done by the pump, that is 2 horsepower, and only 55% of this work goes into pumping. So this much work enters into the water. The work done by the pump on water. So we have to write the value with the negative sign. 2 horsepower, and only 55% of it is used. So we have to convert horsepower units to BTU per hour so that we achieve consistency in our calculation. So how will we do that? Let's multiply this factor, that is 33,000 lb force feet per minute by 1 horsepower. Then we have to convert minute to hour. 60 minutes is equivalent to 1 hour, and 1 BTU is 778 feet lb force. So when you solve it, you should get 2800 BTU per hour. So this is the net heat exchange, is the net work done. So we have to just simply uh, add these values, okay, and we will get the enthalpy. But that is not the end. We have to calculate the temperature of the water that gets changed when this heat is added. So from the enthalpy, we'll be able to calculate the temperature, right? So first let's calculate the enthalpy value. The initial expression was delta H cap as delta E cap is equals to Q minus W. Delta H cap is equals to Q is 5000 minus 2800 minus 386 BTU per hour. Delta H is 7414 BTU plus per hour. Alright. Here we won't use the term hat because we have the units are not per unit mass. Yeah, this is correct. This is your net change in enthalpy. Then what is the increase in temperature? So for incompressible fluids, delta H cap is CPdt, integral CPdt, or Cp delta T. So for water, Cp is actually 1 BTU per LB per degree Fahrenheit. So we know the value of delta H, right? We know the value of Cp. We have to calculate delta T. All right. But first, let's convert enthalpy as specific enthalpy. So we know enthalpy value. It is 7414 BTU per hour. Total mass that is going in the water is 166 lb per hour divided by 166 lb per hour. So this converts the enthalpy value into a specific enthalpy value. Right? Then what will be delta T then? Delta T will be equals to 4.45 BTU per LB by Cp. Cp is 1 BTU per LB per degree Fahrenheit. We cancel out the common terms and we get 4.45 degree Fahrenheit. Okay. So this is the net change in temperature. So initial well water had temperature of 35 degree Fahrenheit. If you recall, this is the initial temperature. Now after change in this much temperature, the final temperature of water, this is the rise, temperature rise. Final temperature becomes 35 plus 4.45, that is 39.5, close 39.5 degree Fahrenheit. This is the final temperature. Okay. So I hope you understood the last question. Now this question number 3, is very similar to the previous one because it it is also an energy balance problem on open systems. Okay, I'll give you a minute to quickly have a read before we proceed. Okay, moving on with the third question on energy balance for open systems. The question that steam that is used to heat a batch reaction vessel enters the steam chest, which is segregated from the reactants at 250 degrees Celsius saturated and is completely condensed. The reaction or the reactants, it will be reaction. The reaction absorbs 2300 kilojoule per kg of material in the reactor. There is some heat loss as well from the steam chest, that is 1.5 kilojoule per second. The reactants are placed in the vessel at 20 degrees Celsius, and at the end of the reaction, the material is at 100 degrees Celsius. So, if the charge consists of 150 kg of material and both products and reactants have the same average heat capacity, that is Cp is 3.626 joule per gram per Kelvin, how many kilograms of steam are needed per kilogram of charge? That is what we have to calculate. The charge remains in the reaction vessel for 1 hour. Okay, so let's begin. So there is a steam chest and heat is basically going in and coming out at 250 degrees Celsius. There is steam, and what is coming out at 250 degrees Celsius? Steam enters, and what is coming out? Condensate, saturated condensate. Saturated condensate. Okay, and there is some loss of heat as well to the surrounding from the steam chest. This is an open system, so the energy balance equation for the open system is as this. U minus W. There is no kinetic energy involved. Delta K cap is 0. Also potential energy is 0. There is no work done here, and energy accumulation due to steam is 0. Whatever energy that is accumulated, it is because of the material, right, that is involved in the reactor. Okay, in the reaction vessel, whatever material is there, there's some energy is getting accumulated. So delta E term is 0 for steam, but it is not 0 for the material. So because of this, the equation changes to delta E material. Now it is equivalent to change in the internal energy of the material. Then minus delta H cap. Here also enthalpy is involved. So this is the enthalpy of steam, and Q. Q is the net heat that is getting lost, right? So this is the final equation after adding in all the assumptions from the question. Now, if we convert internal energy into enthalpy form, then it will be much easier for us to solve the problem. So let's take state 1 as state 1 as 1 subscript. So state 1 we will denote with the subscript T1, and state 2 will denote with subscript T2. Okay, so H T2 plus P V2 minus HT1 plus PV1. This is the change in enthalpy. State 1 enthalpy minus state 2 enthalpy. The right hand side remains unchanged. Let's rewrite for convenience. Becomes this PV2 minus PV1 . Now this term is 0. Why it is 0? Because first no data is given regarding volume change or anything like that. But even if data was given, it would have been too small. So if we are neglecting it, the final expression becomes HT2 minus HT1. equals to minus delta H cap steam plus Q. This is the final expression that will help us to solve the actual answer or get the actual answer. Now, let's consider a basis of 1 hour of operation. During this 1 hour of operation, the heat loss. What is the heat loss? Q is 1.5 kilojoule per second. So in 1 hour, it will be, if we solve it, we'll get the heat loss in 1 hour, which is minus 5400 kilojoule per hour. We don't need to write per hour because the basis is 1 hour, so it's fine. Then what is delta H steam? Delta H steam is basically enthalpy at 250 degrees Celsius or saturated steam. So we can easily get this value from the steam tables. So this is the steam table that I have here. All right, and if you go to pressure table and find for the temperature 250 degrees Celsius, there you go. This is for temperature 250 degrees Celsius. This is the entire row. You will see the heat of evaporation that is required for the condensation to happen is 1712.9. Okay, that is what we'll take here as delta H steam. So it was a negative sign, so it will be minus 1713. Yeah, 13 is fine. Kilojoule per kg. Okay. Now, if you look at the for the material, what is the net enthalpy change? So we are considering the enthalpy for material. We are considering enthalpy at 20 degrees Celsius to be 0 for ease in calculation. So, and before 20 degrees Celsius, this is basically your HT1 at state 1. Okay. And change in enthalpy can be also written as this. The final temperature, final temperature of the material at state 2. Sorry, state 2. State 2 temperature is 100 degrees Celsius. Okay, this is state 2, this is state 1. So 2200 Cp dt. Okay, this is the change in enthalpy. We know the value of Cp, and net change in temperature is 80. Now we can calculate, not this is in terms of specific enthalpy. We can calculate enthalpy by multiplying with mass. So what is the net mass of the material? It is 150 kgs. So 150 kg into Cp. Cp is, from the question, it is 3.26 joule per gram per degree Celsius. I'll quickly reshare my screen. Okay. And we have to convert, since the unit here is kg, so 1000 grams is equivalent to 1 kg. So the value that you will get after solving this expression is 39,120 kilojoule. This 1000 multiple I have combined with joule and written it as kilojoule. This is for material. This is the net change in enthalpy due to rise in temperature of the material. That is, mass of the total mass of the material is 150 kgs. For that, it is the enthalpy. Now we also know that due to the reaction, some heat is absorbed. All right. So if some heat is absorbed, that was around 2300 kilojoule per kg. So for 150 kg of materials, how much heat is absorbed? Heat absorbed 150 kg into 2300 kilojoule per kg. So it will be 34500, 3,45,000 kilojoule. Now we are adding a negative sign here because heat is lost from the system, right? Heat is lost from the steam, which is why we are adding a negative sign here. I hope now the screen is visible. All right. So we have calculated some parameters till now. We know delta H steam, okay. Then we know net change in enthalpy in this side. Q is also we know, all right. So let's put these values here in this expression. So delta H, that is the heat, delta H material is 39,120 kilojoule. Then the enthalpy of steam, net change in enthalpy of steam that we got from the steam table is minus 1713. But since there is a minus sign in the initial equation, so the final term will become positive kilojoule per kg. Now here, this net change is for skg. Let's consider a variable s. So for skg of steam, we don't know the weight of the steam. And there is loss of heat as heat being absorbed by the material, and there is a loss of heat due to the operation, all right, to the surroundings. So it is minus 5400 kilojoule. So if you solve this entire expression, so let's quickly try to do it, then you should get the value of S. So let's quickly do it. So 389,520 divided by 1713 S. So 520 divided by 173. So you are getting S as 227 kg of steam. Now, since you are asked in this question to determine how many kg of steam needed per kg of charge. So the charge is 150 kg. So kg steam per kg charge will become 227 by 150. So it is 1.51 kg steam per kg of charge. So there you go. This is the answer. All right. Now let's move to the next question. Question number 4. This question is again on open system energy balance. You are given two streams of water that are mixed to form a feed to a boiler. The process data are as follows. So let's try to imagine this particular or to represent this particular system in form of a diagram or a flow chart. This is your boiler. There is some heating element. Let's add heat. There is feed 1, feed 2, and you get one outlet. All right. Feed 1 is 120 kg per minute. It is entering the system at 120 kg per minute. One 20 kg water, which is in liquid state, per minute at 30 degrees Celsius. Whereas feed 2 enters at the mass flow rate of 175 kg per minute at 65 degrees Celsius. Okay. And if you do a simple mass balance, you will know that the sum of these feed streams will be the will give you the net mass flow rate in the outlet. So it will be 295 295 kg water vapor. Now this is a boiler, right? Vapor will come out per minute. And the pressure at the outlet is 17 bar. Okay. What we have to find, also one more thing is given, that the exit stream emerges from the boiler through a 6 centimeter internal dia pipe. So calculate the required heat input in the to the boiler in kg per minute if the emerging steam is saturated at the boiler pressure. So we have to calculate the required heat, the Q, and the emerging steam is saturated. Now, if we quickly look at the steam table, we can find the values of enthalpies quite easily. So for feed 1, what is the enthalpy? Here's the steam table. The temperature that it was in was 30 degrees Celsius, and the speed that was entering, it was a water, means a liquid state. So 30 is the rho for 30 degrees Celsius. So we have to take enthalpy value at water, which is 125.7 kilojoule per kg. 125.7 kilojoule per kg. Similarly, for feed 2 at 65 degrees Celsius, the enthalpy will be obtained through interpolation, because 65 lies between 64 and 66. So if we quickly do interpolation, do you know the formula of interpolation? It is y is equals to y1 plus x minus x1, y2 minus y1 by x2 minus x1. So here 64 at 64, your enthalpy of water is 267.9. At 66, enthalpy of water is 276.2. You have to find the enthalpy at 65 degrees Celsius. Right? That is the question. So at 65, enthalpy is, let's say it is Y. So Y1 is 267.9. X minus X1, that is 65 minus 64. Y2 is 276.2 minus 267.9 by X2, 66 minus 64. So if you quickly solve it, you should get 276.2 minus 67.9. One five 267.9 is 272.05. This is your enthalpy at 65 degrees Celsius. So let's write it here. H cap is 272.05 kilojoule per kg. Now we have the values. Also, if you look at the pressure that is given, that is 17 bar saturated vapor. If you again look and go back to the steam table for the saturated steam for pressure table, yes, pressure table, there you go. Then you will see at 17 bar pressure, this is the property of the steam. The steam itself is at 204.3 degrees Celsius. That is the temperature of the steam. 204.3 degrees Celsius. All right. This is the values that we got from the steam table. We have to calculate the value of Q, right, in kilojoule per minute. That is the heat flow rate we have to calculate. Now, general equation of heat general equation of energy balance for open system is this. We have already used this expression several times now. Delta E is 0, right? There is no accumulation. There is no potential energy, so this will also be 0. There is no work done here. So we are then left with delta H cap plus delta K cap into mass goes to 0. So if you multiply with mass, they become delta H plus delta K equals to 0. So if we calculate the values of H and delta K, we can get the value of Q. Okay. So let's first calculate the value of delta H. So we are adding a dot in order to represent the time dependency. All right. That is enthalpy per unit time. It is given as net outlet so I hope you are able to make sense, or you're able to make sense out of this expression that I'm writing. Outlet minus inlet. So for the different components that are involved, I represents how many components are there in outlet and how many components are there in inlet. So I also need to mention here the enthalpy of saturated steam that is coming out. So it is 2793. 2793 kilojoule per kg, right? So we have the values of enthalpies for both inlets and as well as the outlet. We have the mass flow rates as well for the inlets and the outlets. So this expression becomes very easy. So for the outlet part, the value becomes 295 kg per minute. Here enthalpy is 2793 kilojoule per kg. This is the outlet part. Inlet 120 kg per minute. 120 125 0.7 kilojoule per kg plus 175 kg per minute is 172.5 kilojoule per kg. So if you solve this, you should get around 7.61 to 10 raised to power 5 kilojoule per minute. This is your enthalpy in as a flow rate. So dot represents the rate at which enthalpy is getting added. All right. For calculation of the kinetic energy, we have to consider that, or it is actually mentioned. It is mentioned that neglect the kinetic energies of the liquid inlet streams. So only we have to consider the kinetic energy for the outlet. A dot outlet So change in kinetic energy is kinetic energy outlet minus kinetic energy inlet. This we have to neglect. So it will be equivalent to kinetic energy outlet. So in the outlet, there is a pipe. We are given the diameter of that pipe. So let's first calculate the area of that pipe. It will be pi r square. So r is 3 centimeter square. And we have to convert centimeter to meters, okay, for the convenience sake. So if you do that, you should get area as 2.83 into 10 raised to the power minus 3 meter square. Okay. Now velocity of the feed that is coming out, u, can be given as the volumetric flow rate by the area. Volumetric flow rate is expressed in meter per second, meter cube per second, and this is meter square. So this will give us the velocity in meter per second. So volumetric flow rate of the outlet can be calculated from the mass and the density of water. So 295 is the kg per minute, that is the mass, and it's in minutes, so you have to convert into seconds. So there will be 60 seconds in the denominator, and the density we have to divide it by density, will come out to be 997. So for space constraint, I'm not writing the exact units, but I hope you will be able to make it out. So the top part will be meter cube, will be in the units of meter cube per second. And the bottom part area, that is we have already calculated, it is 2.83 into 10 raised to the power minus 3 meters square. So you got is 202 meter per second. Okay. So what is then the delta K dot? Is basically K dot outlet. It is half m dot u square. So m dot for the outlet is 295 kg per minute, and u square you just calculated, it is 202 square, meter square per second square. We have to convert it to in terms of joules per minute. So we will use the this particular factor. 1 Newton is 1 kg meter per second, and 1 joule is 1 Newton meter, and 1000 joules is 1 kg, 1 kilojoule. So with this, we'll be able to calculate the kinetic energy in kilojoule per minute, kilojoule per minute. So the final value that you will get will be 6.02 to 10 to the power 3 kilojoule per minute. Now if you just add these two enthalpy and kinetic energy values, you will get the value of Q. So Q dot is then 7.61 10 to the power 5 plus 6.02 10 to the power 3. So if you add these two, you should get 7.67 to 10 to the power 5 kilojoule per minute. This is your Q dot. And that is the thing that you had to calculate, the net heat input required to the boiler. So this is Q dot, you calculate. All right. So let's move to the next question. This is a very simple equation that that discusses the usage of Bernoulli equation. I'm sure you are familiar with Bernoulli equation from the lectures. So here the question states that the water is flowing from a hose attached to a water main at 40 kilopascal gauge. A child places his thumb to cover most of the hose outlet, causing a thin jet of high-speed water to emerge. So if the hose is held upright, what is the maximum height that the jet could achieve? So I'll do the calculations here only. So you know Bernoulli equation, it is the pressure head P1. So P1, so if this is site 1, this is site 2. So from site 1, we can easily write this expression. And for site 2, you can write as P2 plus half rho V2 square rho GH2. This is the Bernoulli equation. This is for site 1. This is for site 2. At site 1, uh, the P1 is at site 1, P1 is 400 kilopascal. So that is 400,000 pascal. Whereas at point 2, the pressure is atmospheric. So P2 is 0. Density of water remains same both sides. V1, which is the velocity of water inside the pipe, let's consider it as 0 because it will be very small. Whereas V2 will be the velocity of water at site 2 here. Water will be kind of stationary for a few seconds, okay, before it starts falling downwards. So here also V2 will be then 0. Here H1 will be 0. All right, this is the axis that we have used. This is 0, H1, and we have to find H2, which is the maximum height. This is what we have to find. If you take all these assumptions and put the values in the Bernoulli equation, you should get P1 is equals to rho G H2 or H max. So P1, you know, it is 400,000. Rho is density of water, is 1000 kg per meter cube, and acceleration due to gravity is 9.8 meter per second square. Okay, this will be the value of H max. So Pascal, which is the unit of pressure, right? We can convert Pascal, sure, and force, I think. Yeah. Pascal to kg. Yeah. So we know 1 Pascal is equals to 1 kg per meter second square. Okay, this information is known. So we can then cancel out kg, meter, and second square. Okay, so this gives H max as in meters, which is 40.8 meter. Okay, yes. So I cross checked. The answer is correct. All right. So there you go. It's a very easy question on Bernoulli's on the usage of Bernoulli's equation. Now you have to do a simple proof to show that for ideal gas, specific heat at constant pressure is equals to specific heat at constant volume, okay, plus R, which is a universal gas constant. This is a very standard question generally asked in thermodynamics. So first we know, so let me quickly reshare my screen. Right. So we know CV is basically delta U cap or delta T cap at constant volume. Okay. Whereas Cp is delta H cap by delta T at constant pressure. So if we rewrite the expression for Cp, where we change enthalpy into internal energy forms, U cap plus P V cap by delta T, constant pressure. Then rewrite it again. So for ideal gas, U is a function of T only. So that means for ideal gas, delta U by delta T at constant volume will be same as delta U by delta T at constant pressure. Okay, because T and V both are constant. So this means this term, the first term in this expression, is corresponding to Cv. And the ideal gas equation, you know, is PV RT. So if you take a differential both side with P constant, this becomes delta V cap by delta T, P constant, R by P. If you just substitute the values in this particular expression, you should get Cp is equals to Cv plus P into R by P. R cancels out. Cp is equals to, so P cancels out. Cp is equals to Cv plus R. Hence proved. Okay. This is your final expression that you needed to find out here. Easy, simple enough. Now let's move on to the next one. So here you have to determine the heat capacity at room temperature for Na2SO4 and 10H2O. And for this you have to use Kopp's rule. Okay. So from the textbook, I have taken this particular atomic heat capacities table for Kopp's rule. This is the table. Here you are, for every elements, you are given the heat capacity values, atomic heat capacity values for solid as well as liquid. So let's use these values here. This is sodium sulfate salt. So for it, there are Na, L is one element, S is one element, O, H. So these are the four elements present. So Na2, S1, O is 14, H is 20. So these are the number of atoms present in this. And now from this particular uh, atomic heat capacity table, we'll find first for sodium. So it is written sodium So for sodium, we'll take 26. Here the units, please note the unit, it is joule per gram atom degree Celsius. Okay, so the common unit, I'll write it here, joule per gram atom degree Celsius. That is the unit in which the heat capacity will be calculated. Then for sulfur, it is again 26. For oxygen, it is 17. And for hydrogen, it is 9.6. You solve these values and then you have to add them. That will be your final answer in joule per gram atom per degree Celsius. Okay. So let's quickly complete it. 52, 26. 238. 192. So let's add it now. 2 plus 3, 238 plus 26 plus 52. So it will be 508 joule per gram atom per degree Celsius. As easy as that. Okay. Yeah. Okay, this is the answer. Now let's move on to the next question. This is the second last question of today's session. So you are given the heat capacity equation for carbon dioxide gas, which is this. It is expressed in the units of calories per gram mole per Kelvin. We have to convert this equation into a form so that the heat capacity will be expressed in calorie per gram mole per degree Celsius. Okay, so basically what we have to do, convert this expression into calorie, the units of calorie per gram mole per degree Celsius. So temperature term will basically get changed. So T, which is here in Kelvin, will get changed into degree Celsius, and delta T, which is in delta Kelvin, will get changed into delta degree Celsius. So it's a very easy problem to do again, just like the last one. Here you know from the question Cp. Now Cp, if you know the definition of Cp, we have already discussed it. Cp is delta H by delta T, or Cp is delta H by delta T, right? So here, that is why we will consider temperature in the form of delta degree Celsius. Okay. we are intentionally making it distinguished by using the term delta, as it will help us in the conversion. All right. So Cp in calories per gram mole per delta Kelvin. This is the given form. We have to convert it to calories per gram mole per delta degree Celsius. Right? This is what we have to do. The given expression is this 6.393 plus 10.100 to 10 raised to power minus 3 t minus 3.405 to 10 raised to power minus 6 t square. This entire thing is in calories per gram mole per delta Kelvin. All right. This entire thing is in the same unit. So we have to change the units of Kelvin, delta Kelvin to delta degree Celsius for T. So 6.393 here for this term. Let's write the unit as this. 1 delta Kelvin is equivalent to 1 delta degree Celsius. Okay. Then for the uh, T term, then we'll go to T square term. Initially it is this. Now since T is there, so 1 Kelvin term will also come. Okay. To cancel out delta Kelvin, we will divide by delta degree Celsius, 1 each. Whereas Kelvin, 1 Kelvin is equivalent to temperature in degree Celsius plus 273 Kelvin. Okay. Similarly, we'll do for the last term, which is T squared term. Now here note, there is T squared, so there will be a K squared term here now in the denominator. 1 delta Kelvin is equivalent to 1 degree Celsius. And here temperature, that is in degree Celsius, plus 273. This whole term will be squared. Okay, to give you this. So if you want, you can cancel out the common terms and see whether you have written the expressions correctly. Okay, yeah, looks good. Now let's quickly add the factors involved with each t and t squared term, and we'll get the final expression. So the first term remain as it is. For the second term, is multiplication of this parameter per term. There is also a multiplication of this parameter. So if you do the squaring here and then adding, the final expression that you will get will look something like this. 8.896 plus 8.24 into 10 raised to power minus 3t minus 3.405 into 10 raised to power minus 6 t square. This is the final expression, and the unit will be calorie gram mole by delta degree Celsius. So you see the factors where we thought only, or where we took only K and degree Celsius, they all got cancelled, all right? And delta degree Celsius came out as an effect. Okay. This is the last question for today's session. So here's 15 kilomole per minute of air that is being cooled from 430 degrees Celsius to 100 degrees Celsius. You have to calculate the required heat removal using heat capacity formulas and specific enthalpies. So you will get these from different type of enthalpy tables. Okay, so let's start. First case. Now if you look at the energy balance equation, that is delta E is equals to sorry. If you look at the energy balance equation for the closed system, then it is becoming pretty straightforward that delta E, which is the energy for accumulation, is 0. Here kinetic energy is also 0. Potential energy is also 0. There is no work done. Okay. So that gives us only Q is equals to delta H cap. Alright. And Q is equals to becomes inlet air, sorry, becomes enthalpy of outlet air minus enthalpy of air that is going in. Now let's assume that the air is an ideal gas. So there will be no influence of pressure and delta H cap. Delta H cap becomes, which is kg per mole, it becomes from initial temperature of 430 degrees Celsius to 100 degrees Celsius, Cp, which is a function of T dt. Now we have to basically find the expression of Cp that will be integrated over this temperature range. So if you look at the enthalpy table and find the equation for air, so this is form 1 equation, this is form 2 equation. Here you are given the constants A, B, C, D. They are mentioned here. And in this table, they have also given an example on how to write this entire expression with the values of A, B, C, and D. So for air, which is a gas, and the unit is degree Celsius. So for air, for degree Celsius, the values of A, B, C, D are as follows. Okay, and we have to write this. We will use this particular form to fit the values of A, B, C, and D. And this is how the fitting will be done. This is an example. According to this example, the fitting will be done. And so after we do that, the integration will be performed. So Cp is 28.94 into 10 to the power minus 3 plus 0.4147 10 to the power minus 5t plus 0.319 to 10 to the power minus 8t square minus 1.965 to 10 to the power minus 12 t cube. This will be your, or this will be the value of dt. Okay, and if you, so this will be the value of Cp. If you integrate over um, over this range, then you should get, you can easily do integration. All right, it is not that difficult. It's a simple equation, and t values will be respectively added here. But let's do it. All right, let's do it. The first term, there will be 28.94 10 to the power minus 3 t. So here t will be, first let's integrate it and then we'll put the values. Okay, this is the integral form after integration, and after we put the values of t here, you should get minus 9.98 kilojoule per mole. So this is a hard way or a long way to calculate the um, delta heat, delta H. So this is basically Q. This is the long way. Now another way is to use the table with calculated enthalpies already. Okay, so let's try that method. So for this, you'll have to use table number 8. There you go. You have to use table number 8 and then find the enthalpies, respective enthalpies of air, let's say air at the required temperature. So we need the enthalpy at temperature 100 degrees Celsius and at 430, means in between 400 and 500. Okay, so if we use linear interpolation, we can find the enthalpy at 430 degrees Celsius. First, let's write the enthalpy at 100 degrees Celsius that we already found. It is 2.19 kilojoule per mole. Enthalpy at 430 degrees Celsius will be obtained from linear interpolation. So we'll use the same formula that we discussed in the previous slide, I mean one of the questions. Okay. So it will come out to be 12.179 kilojoule per mole. Okay. So the net difference will be then final minus initial, that is enthalpy at 100 degrees Celsius minus enthalpy at 430 degrees Celsius. So it is 2.19 minus 12.179. So you got the same value as in the previous question, minus 9.98 kilojoule per mole. But if you compare, the second method is much easier than the first one. So with this, I'll conclude today's session. I have today we have discussed around 10 questions based on the various topics of energy balance. We solved various word problems concerning open system as well as closed systems. We also discussed Bernoulli's equation and also used enthalpy tables to calculate heat enthalpy depending on what the question is asking. All right. So with that, I'll end today's session and I'll see you guys in the next week. Thank you.